This conference will now be recorded.
Thank you very much for the introduction, Carlos. And I don't recognize too many names of people, so I'm very pleased to meet all of you. I'm hoping that some of the ideas that I'll present today will ultimately be useful in Venezuela and will be helpful to you in getting your oil production back up and running at the level that it should be at. I would like to say at the beginning that what I'm talking about today is the technologies that I think, from my own personal experience, are of value and are workable and effective and economic. I have deliberately left out any discussion of technologies where I think they are less than desirable, not workable, and that they have problems. But I don't really think it's my place to say what's wrong in a sort of public forum with other people's technologies that they're proposing. So I've limited my comments to those technologies that I think have a lot of potential for working better than the technologies that we have today. I guess I'm also starting from an assumption that most of you are familiar with steam-assisted gravity drainage, which has been a successful thermal recovery method in Canada and elsewhere. And so I wasn't planning to go into much detail about how SAGD works, but several of the technologies that I'm going to talk about use SAGD as a basis, but they are improvements on SAGD. So with those preliminary comments,
we're losing you, Tom.
Are you okay? Can you hear it?
All right, now yes. Go ahead.
Yeah, I hope we don't have too many transmission problems, but okay. So as I said, I'm presenting those technologies that I think have a lot of potential, and I've left out anything about those projects that I don't think are going to be very good. I'm basing my opinions on understanding that I've developed over the years of how fluids flow in reservoirs in the subsurface. And this comes from many years of working on a wide variety of different kinds of projects, conventional gas projects, unconventional gas projects, secondary recovery projects, thermal recovery projects, and so on. The most promising methods that I think exist are steam additive processes, and those additives are solvents and non-condensable gases. Hybrid steam and in-situ combustion processes, especially using oxygen rather than air, oxygen or highly enriched air, and hybrid resistive electric heating projects along with solvent injection. So those are the three categories that I think hold the most promise for improvement. Currently, we have, for the first time in many years, we have high enough oil prices for companies to actually make a reasonable profit. We've had a lot of opposition to the petroleum industry developing over the last few years. And in Canada, this has resulted in opposition to pipeline development, which has essentially truncated heavy oil and oil sands development, because without export capacity, there's no point in developing more production capability. around the world, carbon penalties are gradually being imposed by governments. And so if you can find recovery methods that reduce the carbon emissions, as time goes on, this is going to have benefit to your oil production operations and the economics of those projects. Generally, public sentiment has been rising against the petroleum industry. Certainly here in Canada it has, and I think it's gradually growing around the world. But at the same time, there is going to be a need for oil production for a considerable period of time in the future, in my opinion. There are many people who would rather not be dependent on oil, but currently all of our infrastructure, all of our systems are based on petroleum production, and that's going to continue for some time. It's going to, even if you desired to get away from using oil production, it's really not possible in the short term because of the time and money that it will take to replace it. So there's a strong need for new recovery technology for heavy oil and oil sands that reduces the environmental impact. And typically about between, let's say, 25 and 35% of the carbon emissions associated with the production and ultimate consumption of the petroleum comes from the recovery operations themselves. So if you can find a recovery method that reduces or eliminates the carbon emissions, then you have potentially reduced the carbon emissions in the overall development, production, and use of the petroleum by about 1/3. And so this would be a great thing, and it would go a long way to improving the reputation of the industry. What we're seeing today is rising oil prices, partly, I think, because of the lack of investment in new production, and also the fact that economies are recovering from the recent pandemic, and this is driving, I think, the recent spike in oil prices. But the world is in transition, trying to move away from the use of coal, oil, and natural gas to the extent possible. So the main motivation in developing new recovery methods is to reduce carbon emissions that it seems most people think are responsible for climate change and the current problems that we're having. Solar and wind power costs have come down substantially in recent years, and so these forms of energy production are becoming very competitive with petroleum. But nevertheless, we're going to see a continued need, I think, for the development of heavy oil resources. And many countries need to do this to sustain their economies. And Venezuela is one of those countries. I think it's probable that the demand for oil and gas is going to increase rather than decrease in the next few decades. And I find it difficult to understand how we're going to replace oil and natural gas for a number of applications, including home heating in northern climates. I mean, I don't know what we would do here in Canada, for example, without natural gas. There is no alternative right now for jet fuel, I don't think. And natural gas is used for a wide variety of purposes in addition to heating. So the challenge is to reduce the environmental impact of the production and at the same time improve the economics. So what we're looking for is recovery methods that reduce capital and operating costs, lower carbon emissions and water usage, maintain high oil production rates and recovery factors, and improve the economics. And this is a very tall order, as we say, a very difficult thing to meet all of these criteria simultaneously. But this is what needs to be done. So if we talk about the heavy oil recovery processes and the way they work, the fundamental problem, of course, is that the heavy oil and oil sands are viscous in the subsurface, and so they don't move very quickly. They don't produce at a high rate. There are two ways of reducing the oil viscosity so that the oil will move faster. One way, of course, is to heat it, and the other way is to mix lighter compounds, such as solvents, with the heavy oil. So these are the two methods that work to reduce viscosity and move heavy oil and oil sands at commercial production rates. Flooding processes such as steam flooding, water flooding, and so on tend to have poor sweep efficiency. So the injected fluids tend to travel quickly through the reservoir and break through rapidly at the production wells, leaving most of the oil behind. And this is because of what's called unstable fluid displacement, because the fluids that are displacing the heavy oil are much less viscous than the heavy oil itself, and so they tend to just finger their way through the heavy oil and leave most of the oil behind. Gravity drainage processes like SAGD work well for heavy oils and oil sands because they avoid the unstable displacement issue. They result in quite high oil production rates and high recovery. And steam is a material that carries a very large amount of heat. So the sensible heat carried by hot water and the latent heat of vaporization of water are both very high, so that steam is the best medium to carry large amounts of heat into a reservoir. And that's why steam has been so popular and why it has been used so much in the past. However, steam generation results in high carbon dioxide emissions because most steam is generated by burning something, typically natural gas. It also requires large amounts of water. So in a typical heavy oil recovery project, the steam oil ratio might be 3 or 4, which means that you have to use 3 volumes of water for each volume of oil that's being produced. And the other major problem with steam operations is that it costs a lot of money. You have to have a lot of equipment for generating steam, for treating water, for treating produced water, for recycling, for separating water from oil on the production side of the operation. So generally, projects like SAGD projects require a very large central processing facility with all of this equipment, and roughly 65% of the capital cost for equipment in these projects is for water treatment, steam generation, and oil water separation. The other problem is that when you inject this much steam that condenses into steam condensate in the reservoir, you now, if your steam oil ratio is, for example, 3, this means that you have 3 volumes of water flowing in the reservoir for each volume of oil that's flowing. And if you look at the diagram on the right, if you're familiar with relative permeability, what this basically does is it increases the water saturation and reduces what's called the relative permeability to oil. And this makes it more difficult for the oil to flow in the reservoir. So you can think of it as, you know, instead of one person trying to get through a doorway, Now you have 4 people trying to get through the doorway at the same time. 3 of them are the water and 1 is the oil. So it makes it just more difficult for the oil to flow if you have that much water flowing with it. The other thing I should mention is that it's quite inefficient in a steam operation like steam-assisted gravity drainage to inject all that energy into the reservoir, having burned natural gas to generate the steam, and then produce hot water almost at the same rate that the water is being injected, and bringing all of that heat back out of the reservoir. So this is a rather inefficient way to do things. An alternative to heating the heavy oil using steam is to mix solvent with it. And when solvent is mixed, all of the mixture is in the oil phase. So rather than having competing phases, so when you add solvent to the oil, of course, it increases the volume of oil, but it's still all oil phase when you have the solvent mixed with it. So you don't have a water phase flowing that's now competing with the oil. You only have the oil phase. So this tends to allow the oil phase to stay at a high saturation and be able to flow at a high relative permeability. In discussing new recovery methods, there are other things that need to be considered, and there are the differences in heat transfer between conduction and convection. So with steam injection, most of the heat transfer is convection. Some methods that I'll talk about use primarily conduction heat transfer, which is slower than convection heat transfer. And then there's also a difference between what's called thermal and molecular diffusion. So if we're injecting solvent into a reservoir, we become dependent on molecular diffusion to get the solvent into the oil to reduce its viscosity. And this type of diffusion, molecular diffusion, is much slower than thermal diffusion. So these two things, using conductive heat transfer and relying on molecular diffusion, tend to slow the process down. But on the other hand, processes that rely on conduction, heating, and molecular diffusion require a lot less capital investment and have lower operating costs potentially as well. So there is a trade-off between these major factors. There's a very complex interplay between the temperature and pressure in the reservoir, the composition of the fluids, and these have an effect on the equilibrium of the fluids in the formation. And there has been some concern recently about the fact that achieving fluid equilibrium in the reservoir is not an instantaneous process. It takes some time, for example, for gases to dissolve in oil or for solvents to mix in oil. And one of the things that the numerical simulation models almost always assume is that equilibrium is achieved instantaneously. And so the simulation models tend to be optimistic because of that assumption. And the other thing is that you need to have a certain type of formation in order for these various processes to work well. Because, if we're talking about gravity drainage processes, which we are for the most part, SAG-D being one of them, you have to have a sufficiently thick formation in order to make this work. Considering that SAG-D requires horizontal well pairs that are about 5 meters apart, so you're using up, and the lower of these two parallel horizontal wells has to be a few meters above the bottom of the formation. So at a very minimum, you have to have 7 meters just to get the wells in place. But then you need a sufficient amount of formation above the well pair in order to have enough gravitational fluid head for the fluids to drain downward. And you need enough oil sitting above each horizontal well pair to make it economic to drill those horizontal wells in the first place. So really, we're talking about a minimum formation thickness of about 15 to 20 meters, or let's say 60 feet, which is a fairly thick formation. And the other thing about the formation is that it needs to have fairly high permeability and porosity without reservoir barriers to vertical flow of fluid. You have to be able to allow the fluids to move up and down in the reservoir for there to be a gravity drainage process. If you have reservoirs that have high water saturation and mobile water, that's not good for any of these processes. It's normally not good for any oil recovery process, whether it's heavy oil or anything else. So there are, you have to look for certain types of reservoirs, because not all reservoirs are appropriate for this kind of technology. So you need thick, clean, continuous, high porosity and permeability, preferably with low water saturation. So, just very briefly, SAGD has been the preferred method for the last 20 years or so for oil sands production, and it works by injecting steam into the upper well in a horizontal well pair. Excuse me, I have to shut this off. And then the oil and water, steam condensate and oil drain down to the lower of the horizontal wells and is produced. So as I said at the beginning, there are several methods that could meet the necessary criteria of lower costs, lower environmental impact, and improved economics, and these are steam additive processes, hybrid steam in situ combustion processes, and hybrid electric heating solvent injection. Now, these processes tend to be technically complex. The third one, the electrical heating solvent injection, is probably the simplest. But anyway, these processes require a level of sophistication beyond that for simple, could I call it, steam injection. But if they can be done properly, they can be quite successful. So the goal ultimately is to reduce the steam-oil ratio, so the amount of steam that's required per volume of oil. And this automatically reduces the carbon emissions and water requirements. And the preferred additives to steam are hydrocarbon solvents or non-condensable gases. It's possible to mix the use of solvents and non-condensable gases throughout the recovery process. It may not be necessary to be injecting them at the same time. For example, solvents could be used early in the process and non-condensable gases later. A properly operated steam solvent process can reduce the steam-oil ratio about 1/3 while maintaining or slightly increasing the oil production rate. In Canada, about a dozen field pilots have been operated with solvent addition to steam, and overall the results have been mixed. Some projects have failed, some have been successful, and in my opinion, the ones that have failed have been improperly designed and poorly executed in the field, and that was the cause of the failures not the technology itself. If you want to see a properly executed test that proved the viability of solvent addition to steam, I've given a reference here to a 2015 paper, and this was one that referred to a pilot project that was done in the Cold Lake oil sands by Imperial Oil. In my opinion, if done properly, there is no doubt that solvent addition to steam is effective and improves the economics of a SAGD project. It's relatively simple in an existing project to add solvent. And if you do that and you reduce the steam oil ratio, you free up or you make available steam to use in other wells. And so the total production rate for the project can increase without significant additional capital investment in facilities. You, of course, need to add equipment for solvent injection and solvent recovery on surface, but you don't need more water treatment equipment to increase the size of the steam plant or the oil water separation equipment. To make it work well, you need to use the right kind of solvent. You need to choose the right solvent, and hopefully the solvent is the least expensive that you can find. You need to use the right concentration of solvent, and this is typically between 10 and 20 volume% in steam. And you need to add the solvent at the right time in the process. In the case of some of the failed tests, the wrong solvent was used, in my opinion. The solvent concentration was often too low, and so it didn't have the desired effect. And it was injected too late in the process, when most of the oil had already been recovered. So it didn't show any real benefit. The solvent chosen should ideally have similar phase behavior to steam, so that the solvent can be vaporized with the steam and can travel with the steam in the reservoir. Gas condensate, which is primarily pentanes, is often a good choice as the solvent. And in Canada, gas condensate is often used as diluent for heavy oil to make it pipeline transportable. So many projects already have a supply of gas condensate on site. It's also quite important in these projects to monitor the amount of solvent being produced in the production wells, because the amount of solvent recovered and therefore able to be recycled has a strong effect on the economics. I think also many of the pilot tests that have been done have reported quite low solvent recovery, but I think in many cases this was because of poor monitoring and sampling and testing, which resulted in inaccurate measurement of the amount of solvent being produced. And then the other thing is that there are strategies that can be used to maximize solvent recovery and thus to minimize the economic risk of adding solvents, which the solvents tend to be quite expensive, and you really can't afford to lose a lot of it in the reservoir. Non-condensable gases have been used for many years and can be quite helpful. There's a company in Canada called Meg Energy that has had quite a bit of success using non-condensable gas additives to steam in the Athabasca oil sands in their SAGD processes. And what they've been doing is waiting until the SAGD production is quite mature, the steam chambers are well developed, and maybe even intersecting the steam chambers from individual well pairs have met in the reservoir. And what this allows is to reduce the amount of steam being injected, and the non-condensable gases are able to rise high in the formation, displace already heated oil downward into the horizontal production wells, and free up steam or make steam available to be used in other wells. So this has been a fairly successful approach for them. Non-condensable gases, by definition, do not condense. And so they are able to continue, like what happens with steam is as it rises in the formation and it cools, it gradually condenses into water or steam condensate. And then because the steam condensate is heavy and dense, it starts to drain downward again. So it's often difficult to get steam right to the top of the formation. But with non-condensable gases, they just continue their upward movement in the reservoir, and they tend to accumulate in the upper part of the formation, displacing warm oil downward, and they provide what we might call an insulating blanket at the top of the reservoir, which protects against heat losses. And they can be used near the end of the process to save on steam. And they can, non-condensable gases can also be used in maintaining pressure at the end of the SAGD operations to keep the pressure from collapsing as the reservoir cools. Many studies, laboratory, simulation, field testing have shown that relatively small amounts of non-condensable gas have a beneficial effect, but you have to be careful, like in the case of water, not to suppress the relative permeability to oil by putting too much gas in. If you, the bottom comment, bullet point on this slide, talks about the fact that that should be three-phase. My mistake there. Three-phase relative permeability, where you have oil, water, and gas flowing together, are very difficult to understand and to simulate properly. But it is known that when gas and water are flowing as separate phases with oil, they both have the effect of reducing the relative permeability to oil. So you have to be very careful not to put too much gas into the reservoir, in a similar way that you have to be careful not to put too much water in. So this is there's been a lot of talk about using direct oxygen-fired boilers, where the mixture of steam that's generated and the combustion gas products are injected together. But this ends up with often too much non-condensable gas, even if you use oxygen rather than air. And using oxygen rather than air eliminates 80% of the gas. Simulation of the behavior of non-condensable gases in reservoirs has been quite challenging because the simulators don't incorporate what's called viscous fingering or unstable displacement, and they also don't have they don't accommodate the time delay for the non-condensable gases to go into solution in oil and water and to reach equilibrium conditions. And so if the non-condensable gases are modeled as being in solution in the liquids, it means they're not in the free gas phase and moving in the free gas phase. Whereas in reality, they really are still in the free gas phase for some time in the reservoir, and so they move very quickly to a different part of the reservoir than a simulation model would say. The main advantage of in-situ combustion over steam is that heat is generated by burning of fuel in the reservoir. and the heat is generated directly in the reservoir. So this eliminates the inefficiency of heat transfer in the boilers on surface, and it also eliminates the heat losses in the surface lines and in the wellbore. In situ combustion typically uses a residual fuel in the formation, either unrecoverable residual oil or hydrocarbon coke that's formed by pyrolysis. And so there's essentially no cost for fuel in the case of in situ combustion. But there are many problems with in situ combustion, pure in situ combustion processes, as well as hybrid steam and in situ combustion processes. You know, most people are familiar with these problems and challenges, but it's very important to ignite the oil in the subsurface properly, but having steam present tends to promote that because you're already at steam temperature. It's very important to maintain high temperature oxidation conditions because low temperature oxidation tends to degrade the quality of the oil and produce a lot more coke by pyrolysis than high temperature oxidation. And it's also difficult to control the location and movement of the high temperature region. It's important to protect downhole equipment from high temperatures that can exceed 600 degrees Celsius. And it's if unreacted oxygen is being produced along with hydrocarbon vapors, explosion hazards can be a concern. So these things have to be monitored very carefully and controlled. Other problems with in situ combustion include production of tight emulsions, the production of large quantities of non-condensable gases, so that would be flue gases in the case of air injection, or carbon dioxide in the case of oxygen injection, and high gas velocities in production wells can promote sand production and erosion of downhole equipment. But the main problem is severe suppression of the relative permeability to oil. The use of oxygen or highly enriched air eliminates many of the aforementioned problems by getting rid of the nitrogen. And interestingly, if you inject 9 volume% oxygen with steam, approximately 50% of the energy delivered to the formation, so the combustion of oil in the reservoir, residual oil, let's say, by the oxygen injected, generates 50% of the heat, and the other 50% is injected with the steam. So putting in relatively small amounts of oxygen can have a huge benefit in terms of the amount of heat delivered to the formation. I think I'm going to have to speed up a bit here. This is taking longer than I had expected.
Don't worry, don't worry. You can take your time.
Is it okay? Okay, thank you.
Okay.
So many challenges exist, and these include managing the high temperatures in the reservoir, controlling the location of the combustion zone. There have been concerns about cap rock integrity, that is, these high temperatures increasing the stress in the reservoir and perhaps breaking the cap rocks. I've done some detailed studies of this myself, and what was found was that it's really the pressure that is the biggest risk, not the temperature. So the risk of a hybrid steam combustion process is about the same as a pure steam injection process. There are some unpleasant side products of combustion, such as hydrogen sulfide, that have to be monitored and handled very carefully. And then, of course, if you're going to inject oxygen, you have to have oxygen production and storage facilities on surface, and you have to be able to move the oxygen to the wellheads safely. This can be done and has been done, but it's not a simple thing. and so it requires a certain sophistication in the operation to enable this. A lot of progress has been made in recent years to improve the modeling of hybrid steam and in-situ combustion, and I give a reference here to a paper that appeared last year in SPE Reservoir Engineering, if you would like to refer to that work. Now, I'd like to talk about hybrid electrical heating with solvent. So there have been many different electrical heating processes that have been proposed, and I don't want to talk about those and compare them, but I think for me, the most promising one is to use resistive electric heaters with solvent injection. This method is very simple, let's say, compared to hybrid steam and in-situ combustion. And even compared to solvent addition to steam. And the technology exists. There are electric heaters that have been proven that can run at temperatures as high as 800 degrees C for long periods of time. And the temperatures that are being contemplated for this process are much lower than that. And so presumably these heaters would last a long time, being run at much more moderate temperatures. So the method relies on a combination of mild heating and solvent mixing to facilitate oil production. The original concept was presented in a paper at a conference in 2007, and it appeared in the Journal of Reviewed article in 2010.
We're losing you, Tom.
And I've given the reference to that paper here. Pardon me, lose the.
No, go ahead. Go ahead. Now we'll listen to you.
Is the sound back?
Yes.
Okay, sorry. So anyway, there was this paper in 2010 that you can refer to get an idea of what's being proposed. And this paper talked about refluxing of solvent in the reservoir. And the concept here is that the solvent is vaporized downhole. It rises in the reservoir in a similar way that steam does in steam-assisted gravity drainage. When it condenses and drains downward with the oil, it encounters a temperature above its boiling point, and it re-vaporizes before entering the production well, and then rises in the reservoir again. So this is what's referred to as refluxing. But the whole refluxing concept is, in my opinion, unnecessary, but it is important to be able to recover solvent at the surface for re-injection. In this case, the heaters can be operated at temperatures lower than steam temperature, but high enough to vaporize the injected solvent. And this process could be called solvent-assisted resistive electric heating, or SAREH. And the amount of energy that's required in SAREH is much less than in steam-based processes, and the carbon emissions are significantly less. In fact, if you can generate the electricity in some way without burning a fuel, then there are essentially no carbon emissions directly attributed to the recovery process or attributable to the recovery process. So if you're using electricity generated by hydropower or solar power or wind power or geothermal or something like that, or even nuclear power, you can say that you don't have carbon emissions associated with the recovery process. And if only solvent is injected, then there's no need for water injection or water treatment. So the method relies on relatively mild reservoir heating, but heating sufficient to vaporize the solvent, and the promotion of a rising vapor chamber above the injection well, similar to SAGD. I will say too that there may be a way to use single horizontal wells to do this. It would involve a more complex well completion, but if it can be done with single wells, there would be an even greater saving in capital cost. In this method, formation heating is mainly by conduction, which is slower than convection. But then this slower heating is also partially offset by viscosity reduction caused by solvent mixing. The lower oil production rate that would be experienced with this method compared to steam-assisted gravity drainage, the economics are still better than steam-assisted gravity drainage because there's lower energy input to the formation. There's virtually no water flow in the formation, which inhibits the flow of oil. And the capital costs for water treatment and steam generation, etc., are eliminated. Oil water separation equipment would be minimal or perhaps completely unnecessary, depending on the reservoir. And interestingly, a process like SAREH, if for example, you have an existing steam project with cogeneration of steam and electricity, then you have electricity available. So you could be operating a SAGD process along with a SAREH process at the same time. And there would be, the only additional capital involved would be for the solvent storage and recycling. So by way of summary, I would ask, can we agree that heavy oil production is going to be needed for many years into the future, and that there are opportunities to improve on existing production methods? The motivation for undertaking research and development toward replacing SAGD stems from the high costs of SAGD and its environmental impacts. The promising new processes involve additives to steam and hybrid steam and in-situ combustion and hybrid resistive electric heating and solvent processes. And each of these processes could be added to existing SAGD operations with less capital investment and risk than would be required for an entirely new project. I have done myself a very detailed economic comparison of all the processes and found them to be better than steam-assisted gravity drainage with steam-only injection. All of the processes mentioned have a reduced carbon footprint and water usage, and as carbon penalties rise, the economic case for these new methods is strengthened. At this point in time, in the case of SAREH, for example, it has been tested in the laboratory. Numerical modeling has been done, economics have been done, but the process requires field testing, field piloting. And I think probably ideal places to do this would be in existing steam operations. And there's almost no downside risk, because let's say you have a SAGD project operating, you have to drill some wells to maintain production. You could drill some wells, test out SAREH. If it's not working to your satisfaction, you can just convert the wells to SAGD wells. The other point I'd like to make is that pilot testing needs to be done properly. So at the end, there is no ambiguity about the results. If it fails, it should be very clear that it failed, and it should be known why it failed. Similarly, if it succeeds, it should be known why it succeeded, and there should be no doubt about its success. And this can only be done by very careful monitoring. And of course, it costs more money to do this properly. But it's almost better not to do the test at all, in my opinion, than to do it improperly and leave the situation where you're not sure whether it worked or it didn't work because you don't know what to do next. And of course, for a process like SAREH, you need a reliable and affordable supply of solvent. And ideally, a source of so-called green electricity. And for SAGDOX being the name for a process combining SAGD and oxygen injection, you need a supply of oxygen. So steam additives have been tested in the field with mixed results, although I think the failures have been because of poor design and execution. Hybrid steam oxygen injection has been studied in large-scale laboratory equipment and has been successfully simulated at the field scale, but it still needs field testing. Same with the hybrid resistive electric heating and solvent processes. Laboratory testing has been done, the process has been simulated, but it needs to be field tested. And each of these methods can be tested with existing projects, minimizing cost and risk. And the cost would be lower than those that would be encountered in setting up separate field pilots. Pilots are needed now because it takes some time to develop the pilot procedure, to put the equipment in the field, and to run the pilot for several years to make sure everything is working properly. So there's some urgency to moving forward with testing of these technologies. Advantages, again, are lower upfront capital exposure. Processes like SAREH, because they use a lot less equipment, are potentially applicable to small, high-quality pockets of good resource. They need only a supply of power, some solvent storage, and injection equipment. So the technology could be economic at a small scale. The testing risk is very low. And as I said, wells can be converted back to SAGD if necessary. And then the other thing is, if you were in an existing operation, there's been some talk about using resistive electric heaters for the preheating phase of SAGD before production operations commence. And a test of a resistive electric heating and solvent process could be done, and also gather information about the effectiveness of using resistive electric heaters for the preheating phase. So that ends my presentation, and I'd be happy to answer any questions that people might have.
Thank you, Tom. Thank you for this excellent presentation on processes for enhanced heavy oil recovery. There are several questions in the chat. I will address it to you. Okay.
Okay. Can I see are the questions in Spanish?
No, they're in English.
Can I see them?
Yes, if you open the chat, if you want, let me take you the screen out. Give me a second, so we can. Yeah, give me a second.
I'm trying to find my cursor. Ah, there we go. So,
Can you see it now? Well, I will address, I will read it to you. I will read them to you, okay?
okay.
If you open the chat, there are some questions in the chat, and they're in English. The first one is,
Carlos, how do I open the chat?
there is a small oval circle beside the, in the upper part of your screen, you should have the attendees, is a couple of little persons, a circle, an oval circle, and the setting. If you open the circle, can you see it?
The settings thing?
No, beside the setting, before the setting.
Oh, there. I see. Yeah.
Okay. Okay.
Oh, yeah. Okay.
Okay. The first question is from Ricardo Padron, and he said, "What is the biggest field, the biggest oil-in-place field where SACD has been applied, and how has been the largest, and what's the largest horizontal SESH injector, steam injector well?"
Okay. I think probably the biggest field where SAGD has been applied is the Athabasca oil sands. And I can't remember how many billion barrels of oil are in place there, but it's very large. I think of Canada has something like, you know, acknowledged 160 billion barrels of recoverable reserves, and I think about 120 or 130 billion of that total is from oil sands, which is mainly Athabasca. So it's a very large resource, and it's the only commercial in situ recovery method that has ever been found for the Athabasca oil sands. The wells,
and the largest, the longest oil injector and well injector well?
Well, I think it's possible to drill wells up to 2 kilometers long, but most of the wells that are used are about 1 kilometer or 1,000 meters. And this is partly because injecting steam from surface into long horizontal wells, eventually you get a low steam quality towards the toe end of the horizontal well. So while you can drill very long wells, you can't really inject high quality steam over that kind of distance, you know, sustain it. So a lot of the wells are 800 meters, 1,000 meters long, that kind of thing.
Okay. The next question is a long question. I'll read it to you. It's from Dr. Romero. Well, he said, pleased to hear your excellent talk. He said, in the current stage of recovery of extra heavy oil crudes in the Venezuelan oil belt, the Chinese national oil subsidiary is applying FLUE, F-R-U-E, gas injection, using low volumes of natural gas that is normally flared in the operation to bore and compress down into the reservoir. Viscosity of crude where this process is being applied is in the order of 100,000 centipoise at reservoir condition. The steam injection has been discarded not only for high viscosity, but also for the high cost of securing and disposing of water on the area. They claim great results. Very little is known of the results. The fact they have been 4 years in the area presumes certain success. What can you say? Can you say on the flue gas process in reservoir with very low viscosity at depth of below 3,000 feet and highly permeability and porosity reservoir?
Yeah, that's a very good question. Thank you for that, Evanan. Well, I think flue gas injection can show good results, especially if there's some initial oil mobility. But if you have 100,000 centipoise oil at reservoir conditions, and the gas is probably less than 0.1 centipoise viscosity at reservoir conditions. So you have a very large discrepancy. Gas injection can look very good initially because it increases pressure and can help to push oil out. So the pressure difference between the reservoir and the production well can be increased, and that increases the production rate in the short term. But as I said in my talk, the problem with gas injection, especially large amounts of gas, is the unstable displacement and the fact that the gas will break through into the production well fairly quickly. So, but if you have a very thick formation and you inject the gas at the top, you can get the benefit of the pressure increase, but you keep the gas away from the production well as much as possible. That can be successful. It's sort of like having a gas cap on a conventional oil reservoir. You want to keep the gas away from the production well, because once the gas cones into the production well, all you get is gas production after that. So I would expect that results would be quite good initially, but once the gas breaks through at production wells, all you're going to get really is gas production from that point forward. So it might look good initially, and if you've got lots of wells and you can spread the gas injection around, maybe you could do okay for a while. But I don't think it's a long-term substitute for other methods.
Thank you, Dr. Hardy. There is another question, Dr. Hardy. Would you comment on the technology of in-situ refining of heavy oil, which have been claimed to produce clean hydrogen, leaving all undesirable products in the reservoir? So heavy oil used to produce hydrogen. So heavy oil is used to produce hydrogen.
Well, I'm a little bit familiar with proposals to do this, and my first job in industry was working on a pilot project at Cold Lake, where a combination of steam stimulation, cyclic steam stimulation, and in-situ combustion, including the use of oxygen injection, was used. And in monitoring the produced gas compositions, it was noticed that there was some hydrogen being produced. So there's been a proposal to use in-situ combustion to cause the generation of hydrogen in the subsurface. But one of the problems that maybe a lot of people are not aware of is that when you do gas analysis using a gas chromatograph, you usually use helium as the carrier gas. And so hydrogen, helium and hydrogen are both very small molecules. And in a gas chromatograph, what happens is that you detect the difference between the effect of pure helium stream and the produced gas mixed with helium. So when you have species like hydrogen and helium that are very similar, it's difficult to get an accurate measurement of the hydrogen mole fraction in the produced gas. And as the molecules get bigger and heavier, like for example carbon dioxide and some of the other hydrocarbon components, you can get a much more accurate measurement of the mole fraction of those than you can of hydrogen. So there were some large hydrogen mole fractions measured at that time, up to 14% hydrogen. But since I worked on that project and I was involved in the collection of the data, I'm a little bit concerned about the accuracy of some of those numbers. And more typically, you might see less than 1% hydrogen production. And the other problem is that it comes and goes. You know, it's not kind of a reliable and steady thing. But this, to my knowledge, this is where the idea for hydrogen production came from. So I'm a little bit, you know, I don't want to be, you know, too skeptical about it, but I think this is something that needs to be tested. And you know, the other problem is that if you're going to use in situ combustion to do this, in situ combustion is going to produce a lot of carbon dioxide. And apparently, what the proposal is to use some kind of molecular sieve downhole to allow only hydrogen to be produced. So my concern would be, well, where is all this other gas going to go? Especially if 99% of the combustion product gas is not hydrogen but something else. Where is all that going to go? You know, if it stays in the subsurface, it's going to pressure up the reservoir very quickly and stop the process. If it's produced to the surface, then you've got all this carbon dioxide to deal with. So, so that's what I'm familiar with. I hope that answers your question. Maybe you're thinking of a different technology though, but that's the one that I'm familiar with.
Thank you, Dr. Hall. The next question is there is a field in Ecuador, Pungarayacu, extra heavy crude oil field in Ecuador that seems an excellent candidate for your SAREH process. They have plenty of and cheap hydropower available in the field. However, the wells existing in the field are all vertical wells. How would you go about pilot using existing wells and infrastructure prior to convincing the authority that the process works, both scaling and a higher CapEx investment needed through that the process will work?
That's another great question, Evan, and thank you for that. Well, I think the SAREH process is going to need horizontal wells to make it work well, because it's essentially gravity drainage. But I think it would be possible to use vertical wells that are already there. Communication would need to be established between the vertical wells and horizontal wells. But I think the solvent could be, you know, the process could probably be modified to allow the solvent to be injected in the vertical wells. But, you know, there would have to be communication established between, as I said, the vertical and horizontal wells. But I think it might be possible to do that. It would. I'd have to think about it more.
Okay, thank you. So the next question is, do you know of a trial to alter the rock permeability to oil by the introduction of water solution with oxidizer? And he gave 3 oxidizers. I don't know how, EM-NO4, NaClO, K2CR207, with the purpose of improving the oil flow?
So I think these are agents that would change the wettability, I believe. So if you have an oil wet reservoir, you can improve the permeability to oil by altering the wettability. So yes, that's an interesting idea, but you need to have an oil that is mobile So it has to be of a low enough viscosity that it would be worthwhile to do this kind of thing. Presumably, these solutions, this would be a type of water flooding that would have these wettability altering chemicals in the water that would improve the recovery, change the wettability, and improve the recovery. So you would have to have a heavy oil that was amenable to water flooding, and then I think these things could work. Yeah.
Thank you, Don. And the next question is, what is your opinion about downhole spin generation using radio frequency energy, which eliminate much of the surface facility for spin generation and may save money at the end?
Right. Okay. So this is one of the technologies that I didn't want to talk about at the beginning, because I don't want to say negative things about this, but I guess since you've asked the question, I need to answer it. So the problem that I see with this is that the radio frequency antennas that have been proposed are very fragile, and they don't like the presence of impurities in the wellbore. So, for example, if you have metal fragments or water or drilling mud, or if you don't have a really clean downhole environment, it can be a problem for the radio frequency antennas, and it can cause them to basically arc and short circuit and all of that. Secondly, the penetration of the radio frequency energy into the formation is dependent on the wavelength of the RF signal. So the longer the RF signal, the deeper the penetration into the reservoir. But but it doesn't go very far. I mean, typically we're talking about 2 or 3 meters into the reservoir. And what happens in this process is that the water near the well, where the antenna is vaporized and creates the so-called desiccated region. Desiccated in that it has vaporized all of the water that was sitting there. That water moves out in the reservoir and then condenses, forming a higher water saturation area. And this might be a few meters away from the well. And now, and the way this works is that the radio frequency energy is transmitted to the formation by excitation of the water molecules. So the rocking back and forth of the water molecules themselves creates friction and generates energy. So what you have then, I think what might happen is that you've now got this high water saturation zone a few meters out from the well, and the process is trying to vaporize that water as best it can, but the whole thing is being slowed down greatly by all of this water. The other problem is I spent a lot of time in my presentation talking about how it's best if you don't have water and gas flowing in competition with the oil. So now you have a process where you're vaporizing the water, moving the water. Okay, so that's perhaps another issue. And then the fourth problem is the cost of the radio frequency antennas. There was a paper presented in 2008 by Siemens Corporation of Germany where they were comparing costs of electromagnetic methods and radio frequency and resistive heating and so on. And they stated in their paper that they felt that the cost of resistive heaters would be 1/10, so 10% of the cost of a radio frequency antenna. So, and the other thing is that the resistive electric heaters are so robust, they don't they're not affected by debris in the well, by dirt and drilling fluid and metal fragments and so on and so on. They can handle it, and they've been proven and tested. They're cheaper, they're more robust. So in my opinion, it's better to go that direction than to use RF. The other thing about RF, of course, is the more water you have in the formation, the more of a problem you're going to have, because you have to vaporize the stuff with the RF energy.
Thank you, Tom.
Is that sufficient?
I think so.
Reason to not like it? I don't know.
The next question is, can you give an example of non-condensable gas?
I think the best example is the one I mentioned with the MEG energy, where they're using non-condensable gas late in the SAGD process to continue the oil production rate, to keep the oil production rate going, because there's a lot of warm oil that hasn't been produced that is being displaced by the non-condensable gas, and this allows the company to cut back on steam injection to save steam and to use steam in other wells by using the non-condensable gas. So I think that's, to me, that's the most successful application.
What is your opinion about using high pressure vaporized oxygen peroxide to substitute steam for EOR? I think the person that asked the question said that they have seen some successful tests in a Mexican company.
Vaporized oxygen peroxide to substitute steam. Wow. Ooh. I actually don't know anything about that. I have to admit. So I really can't say. That's a very interesting idea. So this is a peroxide solution. Is this hydrogen peroxide, maybe?
Say oxygen. Let me see if Armando has a question. I don't know if you can clarify. Armando, ¿puedes clarificar la pregunta?
Yes, I mean this is hydrogen peroxide, really. Sorry, and this is they used a portable truck to heat it in a pump, and then to inject it to the reservoir as steam, and then that increases up to 5,000 psi the pressure while cleaning the whole area, the whole downhole, and improve the production immediately.
Oh, I see. Okay. So maybe the greatest benefit of it is removing precipitates and things that might be blocking the production well. Is that right?
Yes, that's one of the effects. But in addition, it reduces the viscosity of the oil. It used on the heavy oil. This reduces the viscosity of the oil, increasing the production within the next 2 days by something like 50–60%.
Wow, I see. So the if it's hydrogen peroxide, so it actually dissolves in the oil like a solvent.
That's correct. If I can get your email, I could forward you the presentation.
Sure. Yeah, my email is tgharding@gmail.com.
Good, thank you.
Thanks for that. That's an interesting idea. So and I guess it would depend on the cost of the hydrogen peroxide. as well, you know, how that would compare with other solvents. But,
Okay, just to give you an idea, this idea of this event started, but way back on the late 90s, when they invented one of those ways of propulsing people up to the air by using jets with this formula, and then he decided to do it on the oil wells now in about 4 or 5 years ago, and they have been very successful with that.
Okay.
Okay,
Very
thank you,
interesting.
Armando.
Thank you for
Okay.
that.
The next question, Tom. In situ upgrading technology using nanos reactor and hydrogen has been proposed as a recovery process. What is your opinion about the practical use of this process?
So I think it's technically possible to do this. The difficulty always in the subsurface is it's hard to control where things go, and you have to be able, if you're going to do if you're going to inject nano catalyst into the reservoir, you have to be able to get that nano catalyst into where the oil is. And often, because of the high viscosity of the oil, it's very difficult to do that. So it's like on the surface, if you want to do some upgrading process using a catalyst, and then you have a reactor and you can control where the fluids go relative to the catalyst and so on. The problem in the subsurface is it's much more difficult to do that. So you to make it successful, you have to be able to place the catalyst and the hydrogen in the right place with the right temperature. So this is very challenging.
Thank you, Tom. There is a question here. If not in the, you won't see it in the chat though. Was addressed directly to me. It's a very general question. I say, what is your opinion about the best processes to use in the Orinoco oil well after the coal production finish?
Okay. Well, I think my opinion would be to use something like the SAREH process, because it may be possible to use a lot of the existing well bores. But of course, you have to have available electricity, and you have to have solvent availability. But it's probably the simplest and easiest thing to do, and it requires the least new facilities. So I think that would be a kind of quick way to get things improved and get oil production rates back up again in a very economic way. That's what I think is most promising. If there are steam projects already in place, then various additives to steam, you know, solvents and non-condensable gases and even oxygen can be considered an additive. Those kinds of processes can be considered if there are, but in the primary heavy oil production in the Orinoco, I think the simplest thing might be something like the SAREH process.
Thank you, Tom. The last question on the chat is, would the steam in situ combustion using air promote corrosion in the tubular?
Yes. Yes. When you use in situ combustion mixed with steam, then you get some corrosive products. Yeah, I forgot to mention that, but so there has to be some. Often in a process like this, you would have to inject some corrosion inhibitor downhole, so that the production wells and the flow lines on surface, etc., are protected, because some of the combustion products are acidic and are corrosive. So yes, you would have to take precautions against that, and that of course increases the costs. So all of these things, like difficulties with emulsions and corrosion and erosion of equipment and this kind of thing, they have to be considered in the economics and in the operation. And I think it's part of the reason why there haven't been that many combustion projects that have been successful in the past, because these things have to be properly accounted for and dealt with.
Okay, Tom, thank you. Well, this finished with the questions in the chat. I had one person that requested to make a question alive, Banan.
Perdón, Carlos, ¿sería posible que él comentara la pregunta de Jay Roth?
¿De quién?
Jay Roth.
Que no la vi, disculpa. I'm sorry. Jay Roth, experience with electrical downhole heating cables without solvent injection in the Orinoco heavy oil belt today have produced positive results from 15 to 20% up to 40% increase in production. What percentage increase in production about those levels do you think the additional solvent could provide?
So if I understand, okay. So production has been increased. So this is a production rate. The great benefit ultimately is like when you do, say, primary production, cold heavy oil production, you can do that for a while, but the rates gradually drop off and then you end up having to stop. But when you use a gravity drainage process, you can get up to 60% oil recovery. So rather than getting 4 or 5 or 10% recovery, you can increase the recovery greatly. And if at the same time you can increase the production rate, that's fantastic. So I think the using solvent injection with mild heating, if it increases the production rate by 15 to 20 and up to 40% increase in the production rate, and also can, if you can get some kind of gravity drainage going and increase the ultimate recovery, you can continue like this for 10, 15, 20 years, rather than having the production decline and finish within 2 or 3 years. You can go for a lot longer.
Okay, thank you. Okay, so now I'm sorry, Jay, I didn't see your question. It was the last one. Now, Evan can have your microphone and ask two questions to Mr. Arthur.
Okay, gracias, Carlos. Thanks, Tom, for your complete answers. However, and you know me, I have another question for you related to your answer to the first question. Mm-hmm. On the flue gas, I think you kept saying gas, but actually what we inject is CO2 and nitrogen, because we produce in a unit a combustion, and we keep the mixture of both gases and inject it into the reservoir. What is the advantage over gas? Basically, nitrogen, which is almost 78–80%, is non-condensable, is non-soluble, doesn't get soluble, doesn't dilute into the oil, and it keeps pressuring the reservoir and overall pressuring the CO2, which is the one that needs to go into the heavy crude once the temperature starts working in reducing its viscosity and get soluble into the heavy oil and swells it, increase the volume, and then the nitrogen works as a piston and displaces it back and you produce it like in any cyclic injection. So we are aware of the disadvantage of natural gas, absolutely, but we stay away by injecting CO2 and nitrogen as components of the combustion of the natural gas. Okay, I have another one related to the SAREH, but I wait until you answer this, and if Carlos gives me another opportunity, I will probably discuss the SAREH later on.
Yeah,
okay.
We can do it. Go ahead.
Okay. So, this is as you know, a very complex subject. So, you know, it's true that nitrogen is mostly insoluble in oil and water, has very low solubility in both. Carbon dioxide has very high solubility in both oil and water.
Yes.
So that's you know, in a sense, that's a drawback, because when you inject CO2 and you're hoping that it's going to go into solution in the oil and cause swelling and viscosity reduction in the oil, some of that CO2 is going to go in the water. So its effect is less than it would otherwise be. Like, and methane, the other option, is quite soluble in oil but not in water. So you have this this complex phase behavior issue that has to be considered, and of course the solubility of all of these gases in oil and water is affected by temperature and pressure. So the higher the pressure, the greater the solubility. The higher the temperature, the lower the solubility of gases in oil and water. So so it's a complicated issue, and of course in reservoirs the pressure tends to be fairly uniform, but the temperature does not. If you're using it's not uniform if you're using a thermal process. You know, generally I guess I've been, I don't know whether it gives me any credibility or not, but this was actually the topic of my PhD studies. How many years ago was that now? 40 years ago or so. And I did work with steam flooding with non-condensable gas additives, and I was basically using carbon dioxide, so pure carbon dioxide, as and this project originated because at the time, in the late 1970s and early 1980s, people were talking about using downhole steam generators. So they were the first concept of injecting steam and flue gas or combustion gas products from the generation of the steam into the reservoir. And at that time, very little was known about what this would do to the oil recovery process, to include injection of all this non-condensable gas with steam. So I did a bunch of lab experiments, and I wrote my own numerical simulation model and matched my experiments, and I've been, you know, sort of involved with this and thinking about it my whole career since. I guess I've come to the conclusion that in certain cases, the use of flue gas, which is a mixture of about 80% nitrogen, 20% CO2, can be quite helpful, especially if you're using it for maintaining reservoir pressure. Like in the case of MEG Energy, at the end of a SAGD project, it can be very useful there. But if you're trying to do some sort of displacement process where you're pushing oil from one well to another, like a steam flood, with a lot of non-condensable gas with it, it's not going to work very well. I mean, you get an increase in production in the short term, but then very quickly the gas breaks through at your production well, and then the displacement efficiency goes down quite a bit. So that's been my experience. But in every case, the things that you pointed out, Evan, need to be considered, and that is the question of the differences in solubility of these fluids in different conditions and in different applications. So if it's done properly, it can be successful, but it isn't universally applicable.
Thanks. Carlos, can I say something else?
Go ahead.
Okay, to your answer, yes, we are considering cyclic flue gas injections, similar to a steam cyclic injection. No flue gas driving, because you are perfectly right. The process works as much better in the same fashion that you do a steam cyclic injection. You inject a slug for, well, it depends on the capacity of the reservoir, the depth and the pressure and so forth, 2 or 3 weeks, fill the volume with the nitrogen and CO2, and then you relieve the well. You open it up, and then you have to repeat the cycle a certain time, depending on the original conditions. Anyway, can I just go to the SAREH?
Actually, can I comment on that, Evan, just briefly?
Yeah, go ahead.
I didn't understand that you were doing cyclic flue gas injection, but the reason that can work, I think, is that when you inject the gas into the formation, it builds up gas saturation near the wellbore, and what this has a tendency to do is to reduce the ability for water to flow into the well.
Yes.
So it has an ability to suppress water production, and that's what you want. But it doesn't have a negative effect on the oil production. So
Okay.
it can help control water production, and actually that means that the oil has a better chance to flow. And that may be the reason why it works.
Okay.
Okay.
Thanks. Okay, Carlos, let me switch to the Pungarayaco, which I know, Tom, we talk about it. The real factor, Tom, is the solvent, the availability of solvent to be able to apply your process, but it definitely works. We'll probably be contacting you sometime. They are still in the process of government change, new phases at the operating company and so forth. But maybe we'll have to try with the existing infrastructure, as you know, vertical wells. Of course, the downhole heaters will be a must, but the solvent is the one that is still not being solved for this case. So I'm glad to hear you today, and certainly we'll probably have call you and so forth, but taking advantage of your excellent talk, just giving you the news. We're still alive.
Yeah, that's good. Yeah, and you can contact Barry Blacklock.
I see him over there.
or Jesus Abud, if you want to get in touch with us to talk further. Yeah, I was going to say too that it almost doesn't matter too much what solvent you use in the SAREH process. It can be anything from as light as propane all the way up to pentane. But what you want is to be able to find the cheapest, most reliably available solvent, and then you have to adjust the operating conditions to suit that particular solvent that you've chosen. But the process will work, with a wide variety of these things. It doesn't have to be one solvent that isn't available, You see what I mean?
Yes.
Okay.
Well, With this, we end the Q&A question, Q&A section. And Tom, Mr. Harding, Dr. Harding, thank you very much for this excellent presentation and conversation. We are very pleased with your performance on this today. You know, I think it was a very technical discussion, very high level. Thank you very much. And we hope to have you in another section sometime in the future. Oh, sure. Eduardo, you want to say something before we leave?
Yeah, thanks very much for giving me the opportunity to talk to you. And I hope ultimately this will turn out to have been some value for people. I apologize if it was a bit too technical, but you know, sometimes you just can't avoid talking about these technical things. It just has to be done that way. But I hope that it will result in something beneficial for Venezuela in the future, and I wish all of you a great success.
Yeah, your technical presentation was very appropriate for this audience. I think that we will get use of all the information you share with us. Also, I forgot to thank you, Jesus Abu, that was the person that made the connection between us and you. So you're welcome to, if you are in the future, you're welcome to our webinar and you can learn Spanish with us.
Ah, perfect.
Okay.
Perfecto. Muchas gracias.